Hi guys, today we will see how we can design XOR gate and XNOR gate using this neural network. The first code which we'll be seeing is just the code implementing XOR and XNOR logic gate using a simple neural network structure from scratch. Like no libraries like Keras or TensorFlows will be used here. Instead, it uses a manually defined layer and a step functions. Now let's go through each of them part by part. Before that, let's recap or let's revise first and then just refresh our memory about some of the basic equations. But for detailed lectures, please go through the link provided in the description to see how the XOR and XNOR gate is designed using the equations. Now let's see the basic equations which we came up to is, first we know this XOR of x1 comma x2. This was written as x1 or x2, okay? And then we perform AND operation between them with the negation of x1 and x2, okay? This was the equation. Then we got to know that what we are doing, we can see from above equation or equation between x1 and x2. And then one equations which we are doing between both is NAND between x1 and x2, and then the output of both is given to a simple AND gate. This is AND, correct? So from here we are getting our output. So this is how a XOR gate was designed. And then we got to know that whatever output comes, if we just negate this output, we get which gate? XNOR gate. So we have to just apply negation to the output equation of y, and then we will get what? XNOR gate. Now we saw that in between we'll need hidden layers to perform this operation. This will be acting as your hidden layer. This is your output layer. This is your input layer. So now we have to find some hidden equations. What were those? We considered H1 for the equation which we got here. What was that? Now, as it is performing a OR operation between x1 and x2 for h1, so we know for x1 and x2 with the OR logic gate, equation becomes x1 plus x2 with the bias of minus 0.5. Again, directly if you come here, you won't understand how it is done. I request you all to go back and see how the weights and biases are set for each of the gates. Separate video lectures have been provided in the description below. Go to those links, study those, and then jump here. Similarly, H2 is what? It is performing NAND. Okay, NAND means nothing but negation of AND. So we know the equation for AND. So we are just negating it. So here we got equation as minus x1 minus x2 plus 1.5. This is greater than equal to 0. So we have two equations here now. Correct? We have what? Two equations here. Then final output is performing what? AND between H1 and H2. So what we'll do is, we know for H1 plus H2 minus 1.5 AND gate equation. This should be greater than equal to 0. So these were the equations which we got from the video lecture for designing a XOR gate. Now we know that negation of y will give me what? XNOR. So now if I take negation of this output, what I am doing? I am just negating this output. What I will get? Negation of y. That is nothing but minus of h1 plus h2 minus 1.5, which becomes nothing but minus h1 minus h2 plus 1.5. This should be greater than equal to 0 for what? For XNOR gate. So these were the few equations which we saw in the previous lecture for designing XOR and XNOR gate using neural network. Now let's go to the code and how we implement each of these equations in a traditional way first. Let's see that. So initially we import the library. So just start by importing a NumPy library here. So this NumPy is mostly used for doing this numerical operations in Python. So that's why we are importing this library. It is not used in this code, but it is better to have it as an optional parameter. Then next, let's define the step activation function. So activation functions are nothing but which converts a neuron's raw value into a binary output. So here this function, whatever my z value will be calculated in the neural network. If this value is greater than or equal to 0, I'll be getting result as 1, or else the result will be 0. So when I get return as 1, that means my neuron is activated, it is fired up, and we have to perform some operation. And if it is 0, that means neuron is still silent, it is not activated and it won't perform any operation. Now let's write a neural network for XOR gate. Here, as we saw in hidden layer, we have two equations, one for OR gate, one for NAND gate. For OR gate, we saw the equation was x1 plus x2 minus 0.5. That means my weight was 1, weight 2 was 1 and my bias taken was minus 0.5 for OR gate. Similarly, H2 was nothing but a NAND gate. So for NAND gate, we just simply took the equation for AND gate and negated it. So the weight is minus 1 and the bias is 1.5. So that I have substituted. So here we have H1 and H2. And then we saw for output layer, it is performing AND operation between these two. So I am just performing H1 plus H2 minus 1.5. Now for each input, we are putting this activation function step here. So this step activation function will decide. Now this whole equation inside it will act as Z. Say my input is 0, 0. Then this whole equation, what it will be? 0 plus 0 minus 0.5. That means the step of minus 0.5. Minus 0.5 value, it will go and call here. My Z value is what now? Minus 0.5, which is what? Less than 0. So here I'll get output as 0. And for input x1 and x2 as 0, 0 respectively, my OR gate won't be getting activated, that neuron won't get activated and it won't perform any task. Similar will happen with H2. In this way, this step function works when we pass some equation as a parameter Z here. So this is how a neural network for XOR gate looks like. Now let's see for the XNOR neural gate. As we know XNOR, here equations for H1 and H2 will remain same as we saw in the XOR gate. Here we will just negate the output. Whatever we got for XOR, we'll just negate it for XNOR gate. And then it will simply return my Y. So these are the functions which we manually defined for the XOR and XNOR. Now let's test these equations. So let me write a testing script for XOR gate first. So first I am just passing the input 0, 0. So this will be my x1 and x2. And then in comment section, I am just writing what output it is expecting. So these are the 4 inputs which I'll be passing to XOR gate and these are the 4 outputs which is expected. Similarly, for XNOR gate, I am passing again the same 4 combinations of inputs and then whatever expected output is we are expecting for this, we are just writing in a comment section. So this is how you can traditionally code for XOR and XNOR gate without any libraries imported here. Now this was one way. Now what if I want to use the libraries like TensorFlow and Keras? Then how it is done? So let's do it. Let's see another code where I am doing the same operation by importing the libraries. Okay, now let's break down the Keras based XOR gate neural network code step by step. So this is a classic example of using a MLP, that is multi-layer perceptron, to solve a non-linearly separable problem using this backpropagation. So what is this MLP and what is this non-linearly separable problem? This I have explained in detail in the video lecture and link I have provided in the description. Now first thing first, let's start by importing some libraries. So first is NumPy library for handling our input and output arrays, that is numerical Python. Then we have this sequential. So from sequential, what happens is this is a Keras model. Okay, this is a Keras model type where layers are stacked one after another. Then we have something as dense. This is nothing but a fully connected layer in a neural network. And then we have input. This defines the input shape explicitly. That is optional in Keras, but it is good to have this feature for good clarity. Okay, now after importing the libraries, let's define the data set for XOR gate. Okay, we know the data set. So we have the 4 combinations of input here, that is 0, 0, 0, 1, 1, 0 and 1, 1. And then we have the outputs respective to the each combination. So this here we have defined input and output for XOR gate. One thing to understand is XOR, that is nothing but exclusive OR, is true when inputs are different and it gives false, that is 0 when the inputs are same. This data set cannot be separated with a single linear boundary. So a hidden layer is necessary here. Now next, let's build the model. So for that, I am taking model as sequential. This initializes a simple neural network model where each layer feeds into the next, like no branching here. Then we have the layers. So here input layer, I am adding an input layer. So that's why I am saying just model.add. So input layer takes two features and then hidden layer has two neurons again. Two neurons, and the activation function used here is sigmoid. So this sigmoid activation function helps to squash the input between 0 and 1. This will help the model learn non-linearity needed for XOR gate. And then next is our output layer, that is nothing but having one neuron, and again activation function used here is sigmoid for binary classification. Next, to compile the model, here we are using the optimizer as Adam optimizer. So this is efficient gradient based optimizer that will adjust the learning rate adaptively. Earlier we saw the stochastic gradient descent optimizers. Now here we have something called as Adam optimizer. There are various kind of optimizers you can run and try and see which is working good for your particular test case. So here I am using Adam. Here loss I am taking as a binary cross entropy. This will measure the difference between the predicted and the actual class for the binary classification. And then the metrics I am taking here is accuracy, which will track how many predictions were correct here. Now to train the model, I have something called as model.fit. So here trains the model on X on Y for 1000 epochs here. So that means 1000 times the whole data set will pass through a model. That is my sequential model. And verbose, I am taking it 0. This will just suppress the training logs, which we see in the output section. Over time, the weights are adjusted to minimize the loss function. And here, why we are taking this 1000 epochs? Because XOR is non-linearly separable. So the higher the number of epochs helps the network learn and correct mappings. Okay. That's why we are taking it 1000. You can just play around with this value. You can reduce the epoch and see the results. You can then again adjust the epoch. You can take more epochs and see what is happening with the loss function. You can plot epoch versus loss for each output and see what you are getting. Now, the next step is just test the predictions. So for that, I am just saying predictions for OR gate, and then I am just using model.predict on the input X. Round I am just using to just round off if I get any value in the decimal places. This predict X will return the probability values between 0 and 1. And then this for loop I am taking for each input to display the predictions what we are getting. So this is another way to write a code using this Keras TensorFlows libraries. Okay, so we saw two types. One was a traditional method where we were explicitly designing, where we were explicitly writing our own mathematical equations to see how each function is developed, how each layer is given some equations, some values for weights, some values for biases. Whereas we saw in this Keras and TensorFlow, this weights and biases will adjust itself automatically by the libraries which we are importing, by the various kind of optimizers we are using, various kind of losses we are considering. In this way, there are some parameters which you can tweak around in this code and then see how the results you can get. Now quickly, let's just run this in a Google Colab notebook. We can see how the output is generated. So this is the same code which we saw for the traditional method to design this XOR and XNOR neural network without any libraries like TensorFlows and Keras getting imported. Here we have manually written the equations and substituted the weights and biases. Now here I have this same code which I have copied here, and I'll just press Shift Enter to start running this cell. And when I run this cell, we can see in the output section for XOR 0 0 we get 0, for 0 1 or 1 0 we get 1, and again for 1 1 we get 0. And then XNOR, you can see it is exactly negated results of XOR gate. So this is exactly mimicking what XOR and XNOR are designed to perform. Now let's see the another code where we are importing the libraries. Here you can see this is the another method. We have libraries Keras here from where we are importing just the model and all the other features. So when I run this, let's see what output we get. So I'll just press Shift Enter. Okay. Now here you can see this is written for XOR gate. One homework here, guys. Change your data set for XNOR gate and see what results you get for XNOR, whether it is predicting correctly or not. Okay, now let's wait and see what results we get for XOR gate. So here we have the results now. You can see for 0 0 we get 0, for 0 1 1, for 1 0 1, and for 1 1 as 0. So this is how you can code XOR and XNOR logical gates using this neural network. I hope this was interesting enough for you guys. If you like this video, please subscribe and keep following for more such content. Again, I am stressing directly coming to this lecture won't help. Just understand how the weights and biases are set for different gates. The links are provided in the description, and if there are any doubts, please mention them in the comments so that we can solve it together. Thank you.